Okay, there are a couple of other circuits involving op amps that have some special applications for certain measurements. And the first one that we'll look at is the differentiator circuit. The differentiator circuit takes advantage of the fact that for a capacitor, current is equal to C dV dt. And so an input-output relationship in the frequency domain for the differentiator looks like B out over B in is equal to minus j omega RC, or minus j omega tau, where the output to input voltage relationship is basically a derivative relationship, and then when you do a phasor transformation, you get the j omega term as opposed to the time derivative. So this is the circuit. If it were a pure differentiator, this capacitor illustrated by the dashed line would not be there. Now that capacitor is added because, as you'll notice, the output over input voltage is proportional to the frequency of the signal. So at higher frequencies, there's a great deal of amplification that occurs. In fact, so much so that for virtually zero input, you can get oscillations at the output that are fairly significant in their amplitude. So because of that, this capacitor is added to stabilize the circuit. You might be taking derivatives if you want to emphasize changes in the signal. You might be taking a derivative if you want to get rid of DC, and for whatever reason the DC offset is variable, and so you can't use a normal like biasing voltage or offset voltage that we discussed earlier in the first video. So the differentiator circuit does sometimes come in handy, and of course it can also be used to amplify higher frequency. Another circuit is the integrator circuit. The typical integrator circuit would not have this upper portion. It would just be a resistor to the input, the inverting input, and a capacitor in the feedback loop. And so the integrator circuit output to input would be when switch 1 was closed and switch 2 was open, basically removing this part of the circuit from being active. And so when that's the case, then this circuit integrates, and the transfer function of output over input in the time domain is the integral. In the frequency domain is proportional to 1 over omega. So at very low frequencies, or DC, you get a very, very large response out of the integrator. At very high frequencies, you get zero response. So integrator circuits are used to smooth the signal. They're sometimes used because the actual signal that you get is the derivative of what you want to measure, and so sometimes even integrator circuits are built into transducers, so that if you're measuring a derivative and you need to integrate that for a physically meaningful quantity, you can do that with the integrator circuit. In this example that's shown in your textbook, this is what he refers to as a 3-mode integrator, where you can have switch 1 open and switch 2 closed. In that case, the circuit is simply DC, and it acts as an inverting amplifier. With switch 1 closed and switch 2 open, the circuit functions as an integrator, and when both switches are open, the circuit just holds a constant output voltage. So the integrator circuit is often used to tone down high-frequency noise. As a general rule, when looking at reducing either DC components or high-frequency components, integrators and differentiators are not the circuit of choice. You typically, in that case, would want to use the low-pass or high-pass filter, because they have the advantage of having a range where the output over input is constant. Unlike the differentiator and integrator, you can see that the output over input is a function of frequency, over all frequencies. The final circuit that we want to discuss is the use of a rectifier circuit. Rectifier circuits use diodes and diodes basically are circuit elements that only pass current in one direction. So what this means is that if you have a voltage reversing and you're, say, taking an output over a resistive element, the current won't flow through a properly oriented diode. So what you do is you use two diodes in what's known as a full wave rectifier circuit, and that allows us to do an absolute value. So if you have signals that have positive and negative components to them, the negative components get inverted, and so you'll only have positive components. Here's an example of what is known as a full wave precision rectifier. When this input voltage is greater than 0, then this amplifier at the top is active because the diodes in that case will pass the current. When it's less than 0, then the amplifier at the bottom becomes active. And then basically you have a single adjustable resistor that's a part of both circuits that allows you to adjust the gain. And so this is obviously this is an old publication, 1974. Rectifiers have been around for a long time. This particular one, basically, if the input looks, here's a good little figure, if the input looks sinusoidal, then the output looks like a rectified sinusoid, which means that the negative part has been inverted and becomes positive. So basically, the rectifier is just taking the absolute value of the signal. So that paper was published in 1974. Here is a paper that was published in 2015. Typically in biomedical signals, rectifiers are most commonly used for EMG or electromyography signals, which measure muscle activity, because you're often interested in doing things like taking averages, and because you have both positive and negative components, your average often comes out to be near 0, which is not really what we're trying to measure. So here's an example of a recent publication for some signal processing done in a EMG application, and here is the full wave rectifier that was used. It's essentially the same circuit as the one illustrated in the textbook figure. It's just sketched a little differently because some software was used to do the sketching. So before concluding this part of the module, I wanted to give an overview from the same publication because it's a nice publication, and you can see in this overview that there are actually a lot of components like what we've discussed so far in this chapter. So there are some sensors that are used to acquire the EMG signal. And then from that point, a preamplifier is used. So a lot of these signals come in very small, microvolt to millivolt range. And so a lot of times you will want to use just a simple inverting or non-inverting amplifier as a stage right at the transducer so that you are not as sensitive to noise and you have a better signal to noise ratio if you have, say, a noisy lab environment. So from the preamplifier, then a high-pass filter is used because EMG signals rarely have meaningful low-frequency components. So this is a case where your preamp and your high-pass filtering are selected specifically because you know your EMG signal is going to be relatively small. At that point, a rectifier is used after the high-pass filtering, and then a low-pass filter is used. And so this is done after rectification to reduce the noise and to limit the signal to frequencies that are of interest for the EMG. At that point, an A to D converter is used, and then the signal is passed to a microcontroller and display unit. All of this microcontroller and display unit often now can also be a computer, because we do have devices that really incorporate all of these steps except the sensor. All of these steps incorporated into one unit that then hooks directly via USB to a computer. So that's become more common now. So that concludes the overview of some of the circuits, the specific circuits that are used in biomedical measurement systems. Most of this, if you come from an engineering background, should be relatively familiar. because these are basic standard circuits, and so there's nothing fancy or unusual used in biomedical instrumentation. The one thing that you often do have that's not illustrated in this figure that is really common when you're making measurements on people, and it's not a part of the measurement system, but it is a part of the instrumentation system, and that is an isolation transformer. And what the isolation transformer does is it passes the signal to the measurement system um, via inductive coupling. So the person is not hardwired to an electrical source or an electrical outlet in any way. So that's pretty common in biomedical systems, and it's not really illustrated in some of these kinds of flowcharts because they're talking about the actual measurement part and not necessarily the instrumentation. So that concludes the information in Module 3.